Hi, welcome to video 8.8a. So we're into a new section now, Introduction to Improper Integrals. So the first thing that you're going to need to be able to do is identify what an improper integral looks like. Some will be very obvious, some not so obvious. So the obvious ones will be the ones with infinities, either in as the upper limit of integration, as the lower limit of integration, or both. So that's pretty obvious. You've never seen that before, an infinity or a negative infinity as a limit of integration. But the other ones are not so obvious, and I'll come back to that in a second up on top. The not so obvious ones are ones like this, where this looks innocent enough to you. You're thinking, oh, I'll just do the ln of x minus 2 and I'll evaluate it from 1 to 3. But there's a major problem with this function in that this function has a vertical asymptote at x equals 2, and yet you're looking at it from 1 to 3. So we're passing by a vertical asymptote, which causes all kinds of problems. So what it means is you now have to look at the denominator, ask yourself, when is this function not defined? And this function is not defined at x equals 2. And then you have to look at the two limits of integration and go, oh my goodness, 2 is between 1 and 3. The other problem is if 2 is actually one of the limits of integration. So whether it's 2 to 3 or let's say 0 to 2, you also have a problem. So you, with your big eyes, are going to have to be very observant and notice that. So you're going to have to ask yourself, is the integrand undefined at or between the limits or limits of integration? Okay, so again, here's some examples. Here's one with an infinity as the upper limit of integration. Here's one with negative infinity as the lower limit of integration. Here's one where you have both. Here you have 1 to 3, 2's between there, and it's not defined at 2. The integrand's not defined at 2. There's 2 as one of the limits of integration. Same thing here, so pay attention. Okay, the key thing about how to deal with an improper integral is you have no choice. You absolutely must change it into a limit. There is no choice here. If you do not recognize an improper integral, and you do not immediately write it as a limit, I cannot give you hardly any points whatsoever. So I don't know how much more I can emphasize that you absolutely must write the limit. Now what you're going to do is you're going to replace infinity by a variable of your choice. Of course, x would not be a good one to choose in this particular case, but any other variable. S, T, A, B, whatever you'd like. I'm going to go with A. So what we do is we replace the infinity with a, and then we say, let's talk about the limit as a goes to that famous infinity. And then what you're going to do is you're going to have that limit on the outside, and you're actually going to integrate this and evaluate it from 3 to a. So let's pretend that the integral of little f of x is big F of x. So I'll integrate little f of x to get big F of x. I'll evaluate it from 3 to a, which will give me f of a minus f of 3. Now the whole time this limit stays here. What will happen is this will be the limit as a goes to infinity of f of a minus the limit as a goes to infinity of f of 3. Now keep in mind that no matter what the function f is, if you replace all the x's by 3's, you're going to get a constant. So the limit as a goes to infinity of a constant, that's just a horizontal line, so that's just going to be whatever that constant is. But this is the one, because it's a limit, it might exist or it might not exist. And here's what happens. If it exists, then we're going to say that the integral converges to that particular number, whatever that number is that definite integral equals. Because if this does equal a number like 7 or 0 or half or root 3, then that's what we say the integral is equal to. On the other hand, it might not exist. It might go to infinity or negative infinity or just plain not exist whatsoever. If that's the case, then we say that the integral diverges, okay? You will not write that it equals infinity. You will say that it diverges. Now I want to kind of give you a visual. This would be the integral from 2 to infinity of x squared dx, right? The end area under the curve between 2 and infinity. You can see as you move along to the right forever that this area is just going to get larger and larger. But we will not write infinity. We'll just say that the improper integral diverges. Now, what's interesting is when you look at this graph, if I went from 2 to infinity, found the area bounded by the curve and the x-axis, would that converge or diverge? And I can tell you this, you will never be able to tell by actually looking at the graph. You're going to have to actually do it algebraically. So here's an example. What's the integral from negative infinity to negative 5 of 1 over x squared dx? Now, I will caution you, remember, you should always now be looking, where is the integrand undefined? At 0, right? However, 0 is not between negative infinity and negative 5. But we do have an improper integral. First thing you have to do is you have to write it as a limit. So I'm going to replace that negative infinity by a, and then I'm going to write the limit as a approaches negative infinity. The rest I leave the same. So I'm going to integrate x to the negative 2, which is what 1 over x squared is. That'll give me x to the negative 1 over negative 1, which is negative 1 over x. I am evaluating that from a to negative 5. Remember, don't do anything with the limit until the very end. I'm going to plug in negative 5, then I'm going to plug in a and subtract. I get 1/5 plus 1 over a. Now, the limit is a goes to, I don't care what if 1/5 is 1/5. That doesn't change anything. But if you let a go to negative infinity, this expression will go to 0. And therefore, your answer is 1/5. Now, if we took a visual of this, what the original question was the integral from negative infinity to negative 5 of 1 over x squared dx. This is 1 over x squared, the graph of 1 over x squared. And if you went from negative infinity to negative 5, was it? This actually does converge. If you go on forever, this, the heights of these points will get smaller and smaller and smaller and smaller, and they get small enough, fast enough for the sum of the areas of all the little rectangles will actually converge to 1/5. Now, one thing you have to be careful of, if you have negative infinity to infinity, you cannot, I repeat, you cannot write a, negative a, and let the limit as a goes to infinity. That will not work. I cannot give you any points at all if you do that. You will cry, very much so. I would try to make an unhappy face, but somehow it looks like a mustache. Anyways, so as an example, if you have negative infinity to infinity, you can't write it as one limit. What you have to do is you have to split it up. Now, you could pick any integer or any number, any real number between negative infinity to infinity, but 0 is the easiest. So you break it up from negative infinity to 0 plus 0 to infinity, and then each of those becomes a limit. So you replace negative infinity by a, you have a limit as a approaches negative infinity, then you write the rest of it down. Over here, I have to use a different letter now, so I'm going to use b. Limit as b goes to infinity. Now in each case, if you remember, this is going to give you an inverse tan. I pull the 3 out. My a squared is 9, so my a is 3. My u squared is x squared, so my u is x, so my du is dx. And the formula is 1 over a inverse tan u over a, so it's 1 over 3. Sorry, I shouldn't have used a. I'm sorry about that, the same a. Pretend it's a different letter. Inverse tan of u over a, which will be the inverse tan of x over 3, and that'll be evaluated from a to 0. Now, the beauty is you're integrating the exact same thing over here, so we don't have to recreate that same wheel. This one's going from 0 to b. Plug in the 0. I'll have inverse tan of 0 is 0. You should know that. And then I'll have inverse tan of a over 3 with a subtraction between. The same thing here. Plug in the b, minus, plug in the 0. Inverse tan of 0 is 0. Now, what happens if you do the limit as a goes to negative infinity? Negative infinity over 3 is negative infinity. And the inverse tan of negative infinity. Now, remember, when you're looking at inverse tan, think of the graph of tan, but only between negative pi over 2 and pi over 2. So where does the tangent go to negative infinity? It goes into negative infinity at negative pi over 2. So you have negative pi over 2 is pi over 2. the other one, replace b by infinity, I end up with the inverse tan of infinity. On this one little piece of this graph, the only place where the tangent goes up to infinity is at pi over 2. And I do end up with an answer of pi. This integral converts